Unit 2, assignment number 5. This is page 15 in your notes packet. Okay, here we go. Dilation. So what does that word mean when you dilate something, So think about when you go to the eye doctor, if you've ever been to the eye doctor. But if you go to the eye doctor and they dilate your pupils in your eyes, what they do is that they put some chemical in your eye and then they make your pupil become much bigger. Okay, so a dilation is increasing the size of any shape so that the original shape and the new shape are similar. And we're going to talk about that word in a second when we get to similar shapes. So dilation, if you think of just one word of what dilation means, it means that you're increasing. Okay, you're making a shape bigger. And what you're going to be doing is you guys are going to be taking shapes on graph paper and you're going to be dilating that shape onto a piece of, you're going to be taking a shape on a piece of graph paper and then you're going to be dilating it to make it bigger. Okay, so first of all, let's start with the shape here. I'm going to go ahead and draw an x-axis and a y-axis here. And I'm going to carry the x and the y-axis out to 9 in every direction. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. -9. And -1, -2, -3, -4, -5, -6, -7, -8, -9. Okay, and let's plot some points. Okay, so I'm going to go over 2, up 3. I'm going to put a point right there. I'm going to call that A, which has coordinates of 2, 3. Then I'm going to go left 1 to -1, up 3. I'm going to call that point B. That has coordinates of -1, 3. Then I'm going to go left 3 to -3, down 3. I'm going to call that point C, which has coordinates of -3 and -3. And then I'm going to plot point D at 0, -3. D has coordinates of 0, -3. And then I'm going to connect A to B, B to C, C to D, D back up to A, to make a parallelogram. So you can see that this is a parallelogram, what I have just made. And what I am going to do is I am going to dilate A, B, C, D about the origin with a dilation factor. Then I'm going to put in parentheses scale factor of 3. Okay, so I am going to take this shape and I'm going to take shape ABCD and I am going to dilate it about the origin. So that means that I'm going to take the shape, I'm going to move it about the origin so that it has a dilation factor of scale factor of 3. So what that means is that I am going to make this shape 3 times bigger than it is right now. Okay, and the way that you do this is it's actually a very simple mathematical process. Okay, so what you're going to do is you are going to take each one of the points and its coordinates, A, which has coordinates of 2, 3, B, which has coordinates of -1 and 3, C, which has coordinates of -3, -3, D, which has coordinates of 0, -3, and you are just going to simply multiply each one of the coordinates with 3. And the reason why you're going to multiply each one of the coordinates with 3 is because the scale factor or the dilation factor is going to be 3. So essentially what I'm going to do is I'm going to take this original shape here, ABCD, and I'm going to stretch it so that it's 3 times as long as it is right now. So in other words, like if I started at the origin and I said, okay, that's how long it is from the origin to A, I am going to stretch that so that it is 3 times as long as what it is right now. And the way that I do that is I multiply each of the numbers, each of the coordinates of each one of the points by 3. Okay, so what that does is it's going to change my new point for A, which I'm going to call A prime, as 2 times 3, 6, 3 times 3, 9. And then I'm going to plot that point over 6, up 9. I was a little bit off when I was describing it here. So that's where the point, so that means I'm going to stretch that just a little bit further right there. So that means my A prime point is going to have the coordinates 6 and 9. Okay? And I'm going to do the same. So B, I'm going to multiply each of the coordinates by 3, my dilation or my scale factor, and that's going to give my new point B prime of -3, 9. Okay? -1 times 3 is -3. 3 times 3 is 9. So I'm going to go left 3. I'm going to go all the way up to 9. I'm going to put a point right there. That's going to be my B prime point, and its coordinates are -3, 9. Continuing the process to find C prime. -3 times 3 gives me C prime's coordinates of -9, -9. So I'm going to go left 9, down 9, and that's going to be my C prime point right there, which is -9 and -9. And lastly, I'm going to do the same to find my D prime point. So 0 times 3 is 0. -3 times 3 is -9. So D prime is going to have the coordinates of 0, -9. Okay? And then you can see when I connect the points, A to B, B prime, B prime, all the way down here to C prime, C prime to D prime, and D prime back up to A prime. What you notice is that these two shapes, the original parallelogram ABCD, is similar with my new parallelogram A prime, B prime, C prime, D prime, except for my new parallelogram is 3 times bigger. Okay, so going back to our definition of dilation, it means increasing the size of any shape so that the original shape and the new shape are similar. So there's an example of how we make a dilation and how we set it up on a graph. Okay, so now let's go to similar figures. So the definition of what similar figures are similar if, number 1, they are the same shape, but number 2, they are different sizes. Okay, so similar shape, the definition that we use is that they are the same shape, that they are different sizes, okay? And it means that one shape can be mapped onto another shape by a transformation and a dilation, okay? So let's take a look at what we mean by what does all this mean, okay, and how do we tell if shapes are similar to one another. So, and I'm going to use the example of triangles. So here we have a triangle. Now this triangle may or may not be a right triangle, even though it looks like it could be a right triangle. Without the right triangle markings, we have to assume that it is not. But the sides of this triangle are 6 and 9 and 10. And then we have another triangle which is clearly larger than the original triangle. And in this other triangle here, the sides are marked as, let me finish the triangle first before I get ahead of myself. So we have this other triangle that is larger than the original triangle. And the sides of this triangle are 12 and 18 and 20. Okay, 12 and 18 and 20. And so now the question is, are these triangles similar? Okay, are these triangles similar? Okay, well, there has to be two things that have to happen. They have to be the same shape. Yep, they are the same shape. They're both triangles, but they have to be different sizes. And they are different sizes, okay? And then it says one shape can be mapped onto the other shape by a transformation and a dilation. So what it's saying is, can you take this small triangle and can you rotate it or reflect it or translate it and then dilate it to make it be mapped completely perfectly on top of the other triangle? And the answer is yes. What you would do is you would take this little triangle. First of all, you would flip it over and then you would rotate it a little bit around. So what you can see is that when I do that, the 6 would map to the 12. The 9 would map to the 18, and the 10 would map to the 20. Okay, so what we have here is that we have the 6 would go to the 12, the 9 would go to the 18, and the 10, the side that's 10 in the small triangle, would be mapped to the side that's 20 in the big triangle. Okay, and if you notice, when I wrote out the mappings of what side corresponds or matches up with the other side, all three of these sides, they all reduce to 2 over 1, or 2. Okay, so what that tells me is that these shapes are similar, and the reason why they're similar is because they can all be mapped onto each other, and this 2 is what we call the dilation or the scale factor. Okay, so sometimes the book uses the word dilation factor, sometimes the book uses the word scale factor, but the scale factor would be 2. Okay, and what we're saying is that when the scale factor is 2, we're saying that that side is 2 times as long as that side. And we're saying that, and that stays the course throughout each one of the sides. So the side that is 18 would map with the side that is 9. It's 2 times as long. The side that is 20 would map with the side that is 10. It's 2 times as long. Okay, so when this happens, these shapes are going to be similar to one another. All right? Okay, the last example is kind of a review where we're going over area model, and then we're writing our area model as a sum, and we're writing our area model as a product. So go ahead and in your notes, we're going to draw a rectangle, and then we're going to divide this rectangle up into 4 individual rectangles. Okay, and then I'm going to give you some information about what is on the inside of the rectangles and the outside. So this bottom left rectangle has an area of x squared. The top right rectangle has an area of 24. The top part of the outside rectangle has length of x, and then the left top has a length of 4. Okay, so what we're saying is that all of these sides that I'm highlighting in yellow have a length of x. All of the sides that I'm highlighted in blue have a length of 4. Okay, and then continuing with that process, all the sides that I'm highlighting in green will all have the same length, and we need to find how long those green sides are, and we're going to put it up here. And then continuing that process, all the sides that I'm putting in purple will all have the same length, and we need to find those lengths. They're all going to be the same, okay, for the purple. And then we're going to put that out here. Okay, so first of all, we could start, let's start with the 4. So let's jump over to the 24. So since 4 is blue, and I know that to get the 24, I'm going to multiply however long the blue is with however long the green is, but the blue is already 4. What I'm saying is that 4 times what is equal to 24. So this is what I'm asking. 4 times what is equal to 24? Well, that what has to be 6. So that means then that green part has to be 6. And since it's a positive 6, that makes my length of my top portion of my area rectangle be represented with x plus 6. Okay, so my top portion is represented with x plus 6. Okay, so then I'm going to go through and I'm going to use kind of the same idea to find the bottom, to find the purple part of the rectangle here, which would, this purple here, and notice the inside of this bottom left rectangle is x squared. And since the yellow part is already represented with an x, what we're saying is we want to go what x times something. So the yellow part times the purple part is that question mark. What would give me x squared? Well, that would be x. Okay, and since it's a positive x, it means my side length is represented by 4 plus x. Okay, so the top portion length is x plus 6. The side is 4 plus x, and remember, that right there is what we represent. That's the sum. I'm sorry, that's not the sum. That's what we call the product. When we represent an area model, we call that the product. So the product is the length times the width of the entire rectangle. Okay, now let's fill out the other portions of the rectangle. So this top left portion would be x multiplied with 4. So that is 4x. The bottom right rectangle would be positive 6 multiplied with x. So the purple, which is x, multiplied with the green, which is positive 6. That gives me 6x. Okay, so that means my entire rectangle is represented by x squared. I'm just going to go around counterclockwise, starting at x squared, plus the 4x, plus the rectangle that is 24, plus the rectangle that is 6x, and then I can combine the 4x and the 6x together to give me x squared plus 10x plus 24. So what this is saying is, and that right there, that x squared plus 10x plus 24, that is what we refer to as my sum of my area rectangle. Okay, so I have now expressed my area model written as a sum and as a product, and what we're saying is that these two values are the same. So if you took x plus 6 in parentheses and you multiplied it with 4 plus x in parentheses, it would equal out to be x squared plus 10x plus 24. Okay, there we go. There's your notes for Unit 2, assignment number 5.